welcome to Engineers Ireland. This year, unlike last year, we have a lot more time, so we can go at a more respectable pace. Last year we really pushed things. We can also do this in shorter lengths of time. Last year we were taking maybe 3 hours per class. Now, other than that, almost everything remains the same. The same rules apply. To start with, like any other tradesman, a mathematician or an engineer must carry a toolbox. However, he doesn't carry a toolbox that it would be physically in his hands. His toolbox is composed of small methods that would have been the maths learnt several years beforehand, but now, instead of being the end product, what they are the little tin openers. Would probably be a good term. The little tin openers that allows you open and solve the new problems. Now, while you can clearly see that there are many different sections in the Leaving Cert maths, the interesting thing is the tools actually can apply in right across many of these different sections. Unless you understand them, you are in real trouble. You're in trouble first off because you may not be able to solve the problem. The second reason you can be in trouble, even if you solved it, it's taking you a lot of time, and you only have a limited amount of that in the Leaving Cert. The first set that I always see as being tools are the how to manipulate and play around with indices. In school, you're generally, you're explained what x cubed is and stuff like that. But the one that will always catch people, and you'd be surprised at what age it can catch people even into their 40s and 50s, is, for example, x to the power of 0. Now, fundamentally what you're taught in school is, for example, we'll write down a series of them here. What you're actually taught is this. And the real issue is, what is that one? It isn't intuitively obvious to you, and a lot of people actually just guess, and sometimes they'll guess 1, sometimes they'll guess 0, but it only takes a small change in how you approach something. In other words, the overall set, there's only a small change that it takes that makes things like this much easier. For me, one of the most useful little rules that we have in maths is that it's possible to multiply anything by 1 without changing it. So let's apply that to these. So x squared is 1 multiplied by x by x. x1 is 1 multiplied by a single x. So x0 should be 1 not multiplied by x. So it becomes an obvious answer, and it gets rid of the guesswork. The other thing you'll notice is each of the powers we've looked at are positive powers, and a small amount of reasoning would have you say, well, if the positive powers multiply into x, I would expect the negative powers to divide into x. That would be a guess, but a good guess. This last one here helps give us one of the rules that you're given for indices. We'll put it up here. So we're basically saying when you have got x to some power, it's equal to 1 all over x to that power only brought to the negative. Now, I've it written in a fashion that you don't normally see it, and I've done it on purpose. You'll normally see things like, and you would say, yeah, that makes sense. But if you look at this one up here, for example, I can say to you that x cubed is 1 all over x to the minus 3. And that's exactly the same as applying this rule here. It often happens that when you're solving problems, you finish up with an expression that looks like this, x to a minus power underneath the line, and you can sit there wondering as to what you're going to do with it. It's exactly the same rule as you would have normally seen before, such as x to the minus 2 is equal to 1 over x squared. Well, what's wrong with saying that x squared is equal to 1 over x to the minus 2? The other thing about the rules of indices is when you know them, you actually only half know them, because you need to see them from both directions, both from the ways they're normally written down from the left hand side, where they will say to you something like x to the m equals, or sorry, x to the minus n equals 1 over x to the n. You also need to learn them from the right across to the left, because most often when you're solving problems, what you actually get is the bit that's on the left hand side. So when you're looking at the problem, you're only seeing half of the rule. So it's important to learn the rules from both directions. Now, the other little rules all pop out from a basic understanding of these things. If you've got x to the n by x to the m, and you want to know what is it, well, something you should always try to do in your maths when you have a problem and it's a little bit more complicated than stuff you're very comfortable with, you go across to the right hand side. And by the way, you do this in the exam also, because what will happen is you have a little problem, you can deal with it over in the right hand side, you can bring back your answer to your main stream of your mathematics, and you finish up with a much cleaner answer. That's important because you need to communicate your answers. There are definitely marks to be gained by good communication, but more importantly, there's a lot of marks to be lost if you communicate badly, because first off, you're just bringing confusion into the mind of the person who is trying to correct what could be a complete mess on a page. Instead, what you should do is mess across here on this side. Even if you get that wrong, so what? Try it again a little bit below it. Just keep away from the mainstream of your maths, which runs down on the left hand side, not over on the right hand side. So if we pick a simple example and we just play out what it actually means, we know it's this. So when we just count the heads here, we find that there's 5 of them, and we know that 5 is equal to 2 plus 3. So our answer over here, clearly, and now by the way, I accept that almost all of you know this as a rule. I'm explaining it simply to show you the process of bringing a simple problem across to the right hand side to understand a concept. So I want you to learn 2 things at once. First off, refamiliarization with the indices, and secondly, this method that I will constantly keep talking about in the next few weeks, where you go across to the right hand side with a very simple problem, deal with the simple problem, it gives you a map. That map tells you how to deal with the main problem. So we can say this is n plus m. Okay? Now, the other one that's a bit similar, x to the n, all that to the power of m. Well, pick a simple example. And you got 6 of them. So now you can fill this in. They're all straightforward. They all come from the first very simple run of just what powers or indices actually mean. Now there's a few others that you need to know. Square root of x. What is it? X to what power? Now you'll notice that I've been using a few question marks. Now in general in mathematics you don't use question marks. I would put in there so that you can see that very often you're left with a little gap and you have to say, well, what am I going to call this? And in general in maths you do name things. Again, naming things is a very, very powerful thing in maths, because once you can name it, you can manipulate it. You can play with it. And I don't care what name. It doesn't have to be nice classical names such as ABCs or alpha, betas and gammas. You can name it Nora or Fred for all I care. Your task is, when you're faced with problems in maths, often when they get complex, if you rename it, you can simplify. Once you simplify it, it's much, much easier for you to go and solve it. So in this case, let's give it one of the more classical names. We'll say the square root of x is x to some power, which we're going to call a. Now what we will do with this thing that we now have over here, nicely named for ourselves, is we will play with it in the fashion that we know gives us the character of the square root of x. We know that if the square root of x was multiplied by itself, the answer is x, and x is itself to the power of 1, of course. So we can say, so x to the 1 must be x to the a by x to the a, which is x to the 2a. So, and that implies that the square root of x is equal to x to the half. Very simple. The funny thing is, over the years I've often asked this question of students, the square root of x, what power of x is it? And in most cases they don't know, but that's not the problem, because in general when we're solving problems in maths, the idea is you don't know what the problem is, otherwise you wouldn't have to solve it. Not knowing isn't a problem. Not knowing how to proceed to get an answer is a problem. So what I'm saying is, so what if you don't know what this is? What you do is you set up a game where, and one of the big things you do is name things, and then you play around with the name thing and you solve it. For example, now that we can see the process, the cube root of x, what is it? Or will you say x to the b? Well, we've it named. Now we can manipulate it. We know that the cube root of x by itself, and again by itself, is x, which is x to the 1. So we can say x to the b by x to the b by x to the b must be the same thing. All I'm doing over here is I'm copying what I've done here. But now we're in a position to be able to say that x to the 1 is equal to x to the 3b, which implies b is 1/3. So the cube root of x is equal to x to the 1/3. Okay? Now, they're the basic rules of indices. Still, there are ways that you can easily get caught out, and they're the ones that you don't commonly see. For example, what's the answer to that? Before you ever rush in to solve any problem, you're supposed to look and see what's there and apply basic ordinary reasoning to it. In other words, you allow your mind to describe what's there. This is different to the other problems. It's not an x to the m multiplied by x to the n. Because what you have is, that's a minus sign. Okay? So you have a term minus another term. Now what we need is to find some way of converting one term to look a bit like the other term. Now if we come over here, again picking a simple example, and we look at, let's say, okay, if we look at 2 cubed and we say, what is that? It's 2 by 2 by 2. So we can say we know what 2 to the 7 is, and we know what 2 to the 6 is. Now the interesting thing is, let's just do it out the very long way, and hopefully you'll never ever have to do this again. That's 2 to the 7. See all that part of it. That's 2 by 2 by 2 for 6 of them. So what we have in there is 2 to the 6. So what we can now say is 2 to the 7 is 2 multiplying into 2 to the 6. Okay? Now, that allows us to solve the problem. This 2 to the 7 minus 2 to the 6, oops, got carried away there. That's actually, let's convert the 2 to the 7 now. It's 2 by 2 to the 6 minus 2 to the 6. Just to make in the Leaving Cert, questions have come up where this is necessary. It isn't just the small section that might possibly come up in algebra where you're actually getting a problem on indices. This type of thing, this little simple way of solving things, comes up in induction, it comes up in calculus, it comes up in 4 or 5 sections that I'm aware of. It'll show itself in different guises. We're looking at 2 to the powers often here, but fundamentally, whether you're dealing with ins or factorial ins, etc., the game is the same. Okay, so let's just pick a slightly different problem. If we go 3 to the 5 minus 3 to the 3, what's our game? Our game is to try and show up 3 to the 5 in a fashion that looks like 3 to the 3. Now we do know it's 3 squared by 3 cubed minus 3 cubed. So we're saying it's 6 3 cubed minus 3 to the 3. You can call that an apple, and that's an apple. 6 apples minus an apple is 5 apples. Exact same little game. Okay? Where else could you get this kind of thing? n plus 1 factorial minus n factorial. Okay? What you have to do is you look to see what you have. Clearly it's a term minus another term. You want to convert one of the terms so that you can play with it, and all you have to know, and we can see it over here just to find out, 4 factorial we know is 4 by 3 by 2 by 1. And you'd say to yourself, okay, but look at this bit. Isn't that 3 factorial? So here we can say that 4 factorial is equal to 4 multiplied by 3 factorial. Now we've got a very simple way of being able to convert the bigger term here into a form that I can take away the smaller term from it. So I'm able to say it's n plus 1 multiplying into n factorial minus n factorial. This could be anything. You can call it Fred for all I care. N plus 1 Freds minus Fred. If there was n plus 1 Freds in a room and 1 left, how many would you have left? You will have n Freds left. So n plus 1 factorial minus n factorial is n multiplied into n factorial. There's at least 3 chapters that I can remember in the Leaving Cert course where this type of manipulation happens a lot. And it's exactly the same thing that we actually did with the indices. The main issue is your job, before you rush into doing anything, your job is to look at the thing, recognize what's there, see how to manipulate it, change names, okay? Because changing names simplifies. Find a simple example just to absolutely confirm in your mind what you're doing. Having learnt your simple lesson over on the right hand side, come back to the left hand side. Obviously, if you're very clear in your mind as to how you should proceed, you don't need to go over to the right hand side and do it. Now that brings me to a different point. What can we expect to get out of these classes? What I can do is I can clarify the mathematics for you. I can bring you to a point where you can say, yes, I understand that. What's your half of the bargain? Your half of the bargain is to turn that and saying, I know that. Bringing it to I know that, that's your job. Nobody can do that for you. But what we can do here for you is we can bring you to the point of saying, yes, I understand this now. The funny thing is, when you do understand something, you actually find that it's actually interesting. Maths is fun. You can also feel just how much ability learning maths can give to you. You can solve problems that can mesmerize other people if you learn mathematics. You won't necessarily see this, by the way, in the Leaving Cert course, but certainly if you're doing the Applied Maths course, and we will actually be running grinds for Applied Maths in here, you will see lots of interesting sort of problems, all solved by very straightforward maths. And again, the secret there is manipulation of basic mathematics that you know already. Here, in straightforward maths, issue for you has to do with how much time should it take. Now, there's a saying about comparing diamonds and coal. Like, one little diamond can be worth more than a ton of coal. It's the exact same with your study time. If you put very little in, you'll get very little out, even from a lot of it. So all you're doing is you're playing with coal. If you know how to study well, you can get a lot out from less time. The objective is not for all of you guys to turn into nerds. That's the last thing we'd want. We certainly don't want to see a generation of engineers coming out in a few years' time and they're all nerds. Because, like all professions, it's very important for us to be able to work in the community, to be able to work with many other disciplines, to be able to talk to people who will have some interest in the project but perhaps not a full line interest. We have to remain focused on what we need to do. We have to be able to solve problems. Well, we certainly don't want to be nerds, so how do you avoid that? Well, if you put in loads and loads and loads and loads of hours of low quality, you will numb down your brain because you're not actually educating it. Now, in the physical world, if you want to go and buy something, whatever it is, it costs you. In this physical world, you pay coinage, and the coinage is money. You want to buy a new telly, it'll cost you money. It's exactly the same in the mental world. If you want something, You can have it, but it costs you. What do you have to pay in the mental world? What you pay is attention. If you really simply place your attention when you're studying, you will get to buy what you're looking at. It gets to go in. If you're not paying attention, if all you're really doing is going through the mechanism of sitting down and doing some study, low-grade stuff, it's like a ton of coal. It's not as valuable as less time spent with attention. You pay attention. Now, just a simple issue in relation to this. Don't get confused when we say attention. We're not talking about becoming so focused that you're literally grinding yourself looking at a small thing. You place attention on something and you leave it on it. It's actually a very light and easy thing to do. Study isn't a particularly wearing thing if you know how to study. Again, if you have studied something, you would expect to be what people would normally say, to be able to remember it. Now again, I would like you to just hear one thing. Especially those of you who think that you have a poor memory. You don't. Everybody has a wonderful memory. Simple proof. Try to forget something. It's almost impossible. It probably is impossible. The more you try to forget it, the more it's in your mind. So what's the problem then if it isn't memory? The problem is recall. You need to be able to recall something or you can't use it. There's no use sitting in the exam saying, yes, 2 months ago I did that. What was it? That's no good to you. You need to be able to recall it, and there's two aspects to recall. First off, it has to go in or it can't come out. And secondly, you have to strengthen your ability to recall. Now, when I was in college, I used to read something, just let's say the first time on something, I'd be reading it, I'd be storing it away in my mind, and I'd be recalling it, and I'd be revising it all at the one time. The process is simple, and it's what I would just say to you, just try, okay? Try it for a few weeks. That is, when you're looking at something and you might only be half a page down, you stop, you leave your hand on the page. Or it could be that it's on the previous page and you don't have to leave your hand down, it's not visible. You ask yourself, for argument's sake, you'd say, what was that equation? Now, in general, what we've let ourselves away with is saying, I don't really remember that. And you accept that answer, and you go back and you flick over the page, or you lift your hand and you kind of look at it and say, oh yeah, that's it, I can see it now. Well, you've just partaken in a game you've been playing for years, and it has almost no value other than it generally gets you lets you get away with saying, yes, okay, I am studying, but it's not really going in. So what's the alternative? The alternative is extremely simple. When you ask the question, what was that equation? You demand from your mind that it gives an answer. It must answer it. It can't just say, oh God, I don't know. It must answer. And when it is answered, you're now turning the page to see that equation that you might have just seen for the first time 15 minutes beforehand. The difference is your mind really looks at it now because it was forced to give an answer. So its attention level has gone up. Now it's a characteristic of us people that we don't like getting caught out. And in study, if you study like this, where you keep demanding of your mind that it tells you what it had seen a little while beforehand, what the equation was or what did such a passage mean, it gets very fed up with this, being caught out. And within literally a few, I suppose even 2 weeks or so of you starting this, what you should find is when you go to sit down to study, that just before you start you find your attention level goes up, which is something you have strengthened because you've constantly demanded that it tells you what something is, that it recalls it, okay? So your attention level has gone up, you've strengthened your recall, and now when you sit down, guess what? You will find for less time, you get more into your mind, and you've practiced recalling it so it'll come back out when you need it for your exam or doing any problems. That is a background, okay? Now what I would say to you is, in the next few weeks, I would really like if you practice this, because I would like to think that we not only will be able to help you understand your mathematics, but that we will help you to do it faster. It is important because time is a consideration in your exam. You get ahead of your time curve. Now all of a sudden you can relax because you've got this freedom. You're ahead of your time curve. You know that even if a future question goes slow for you, you have the time. So what you need is to become effective. And you also need to become effective while you're studying to the Leaving Cert, because no one wants you to become a hermit. We want good rounded engineers and scientists to come through our education system. So it's important that you have time off. It's very important that you have time off. So how do you do it? Become more effective in studying. You must understand something first. Through practice, you turn understanding into knowing. Through demanding of your mind that it recalls something now, you strengthen your mind's ability to recall. By immediately looking at it, after having demanded that it recalls it, you are putting it deeper into your memory. And by the way, as your mind gets better and starts to recall things, praise it. Because like all of the rest of us, we like praise, and our mind will get much happier when we start to praise it rather than constantly kicking it. So let's see if we can have fun over the next few weeks. We will mainly follow section by section. However, we will definitely run off and pick pieces from other sections, and we'll do so because there is a nice amount of interconnect between many of the different sections for the Leaving Cert. Another reason we'll do so is if you look at the past papers, and we will be getting through those by the end of this, what you will notice is often the solution to, for example, a Part C requires you to have a clear knowledge of a different section. That's not an unfairness. Hard that you're now worried about an evening paper. If you can walk out the door of your exam not particularly tired, quite relaxed, you're even guaranteeing a good mark in your next subject. So let's see if we can put that into practice. And for the next one of these classes, we'll start with algebra, because that is the golden key to all of the other sections.